No, it's not. No, not yet. Not yet. Not yet.
I see the car. You might as well just tell her, right?
Yeah. Okay, Jasmine, we're clapping for people who come in late. Technically, you're not late yet. I know. That's why I said don't clap yet. And everyone else just was super eager on the clap. Now we're legally late. Okay, let's start. So she wasn't present and sitting. Oh, you're not sitting. Let's go. Okay. So the first thing that we're going to talk about today is the rest of the schedule. We're getting close. Okay. So this is week 14. As usual, we're a little behind. I think we'll definitely get through Ekman layers. I don't know that we'll get through GeoWaves. You might get through Ekman layers and start being like, bro, this is so dumb. Like, I don't even care at all about the Ekman layers. Oh, shit. You might get into like the geophysical versions and be like, these are really cool applications, but once I saw them a couple times, not so useful, and I want to get right into instabilities or shocks. So I will ask you in the Slack probably to just vote for a poll as to which of these 3 topics, because we only have, my math is correct, 4 more class units to fill your brains with knowledge. That's scary. No one even cried about that. That's okay. Oh my God. All right, whatever. So let's talk today. We said we're gonna see how many slides I had. That was a lot of slides, right? 5. Woo! Crazy. Okay, so we're gonna have a discussion today about Ekman layers, which is a form of a boundary layer between immiscible flows. So either a hard surface or a free surface like the air. This is a version. Is a version of an Ekman layer. We talked a lot about boundary layers. I hope that everyone found that class very instructive. We began to think about the idea of turbulence and the way that we use these equations of motions to understand the world around us. These are the things that you now have memorized and totally understand, right? Mm-hmm. Do we want to do any of them? You want to do bottom one?
I don't.
Well, you just raise your hand, so therefore you are doing the bottom one. If you raise your hand, that tells me I want to learn. I'm so learned today. So what's this one?
Has to do with electricity.
Yes, good. Yeah.
I think it's like direction and
slightly different word. You want to help them out, Rolando? Diffusion. Right? And you can see these diffusion terms, right? What do the diffusion terms look like? They have a Laplace operator. Mm-hmm. So what does the Laplace operator do? Yeah. Sure. But that's a representative of what it means. What does it do? It's a smoother. Oh, okay. Right? So if you have a smoothing operation, you have a Laplace gradient, right? Okay. Does this make sense now? Mm-hmm. So what are the ways that you can generate vorticity? Yeah, according to this equation. That is vorticity. Generates it. Yeah, because remember up here, we said something along the lines of, this is the continuity equation. And let's say I'm explaining it to my deceased grandmother, right? And I'm at her grave and I'm giving her the daily update of what I learned. And I'll say, the continuity equation really means, how can I produce mass, right? And the answer is there's no ways to produce mass in fluid dynamics. I can move it around. So I can, for example, change my density in time by changing my physical density in space. Right? Stuff comes in and it fills up the density there. So that would be the left-hand side. So here I could say the same thing about the momentum equation. How can I generate momentum? And it's all of these wonderful terms that we've grown to know and appreciate, right? The same thing's true of energy. How can I generate internal energy? How can I generate kinetic energy? With all of these terms. So let's use that same analogy. How can I generate vorticity?
advect it from somewhere else?
You can advect it from somewhere else.
Or from the viscosity?
Yeah, the viscosity is here, and it will do something.
It will hold that. Oh,
It will transfer it, good. What kind of transfer?
is it heat? Like I see.
What is this? Laplacian, and Laplacians do what? Smooth, and another word for that is to diffuse. We diffuse things through a fluid, right? If I fart in this location and it gets diffused everywhere else. Is that true?
Yeah.
No, it's not true. Most likely the fart is advected. Why is that? Diffusion slow, advection fast. That's why not everyone smells farts in an expanding radius of time t, right? Usually it's he smells the fart, then he smells the fart, then you smell the fart, then Desiree smells the fart, right? Because there's circulating currents in any room that you can't see or necessarily perceive, but you can smell them. Okay, so I can generate vorticity by diffusing it from other places that have high concentrations of vorticity. And I do that through the viscosity in the fluid, dragging this vorticity away from the places that it's concentrated. Or the fluid is itself moving, and it drags with it vorticity lines and piles them up, generating vorticity in a location. Yeah.
So what was just something adequate for an example? As opposed to like farting, would it be like weather, like weather patterns? Is that slow enough, like the rate itself, or?
Oh, sorry. So you're asking like, what is a good example of a diffusive phenomenon?
Isn't it like something you touching, like wouldn't an example be like you touching something cold and then you just like,
So that would be certainly accurate for solids, yeah.
okay, oh, for solid.
Yeah. For a fluid, yeah, you could still probably do like the beads of sweat on your skin, because the heat will diffuse from the solid boundary into the into the sweat bubble, and then that sweat bubble evaporates, right? That's a diffusive property. But usually we tend to think of it in terms of whether it's heat diffusion in an atmosphere or let's see, what's a better example? Diffusion tends to be really slow. It tends not to be the dominant process in a lot of cases. I'll think about it a little bit longer and I'll give you a better example. Okay. Okay. This is an incomplete list of the things that you've learned. They are in no order other than alphabetized, and in some cases not even alphabetized because I'm not really good at spelling sometimes. So what I want to do for the next couple weeks is, you know, all these, right?
Yeah.
You're pretty confident in them. Do you know these? Nah. So nah, definitely not. So one of the things that we do when we think about communicating physics is we need to use the right words. If I had a feeling of like, oh, I feel like I'm going really fast, right? You could very easily confuse that, let's say you didn't know physics well, with the sensation of accelerating, right? And there is a physical difference. So knowing the difference between the words is helpful in communicating to other scientists, right? So we are going to do that. And maybe we should have started this a long time ago. I just thought about it when I was having a conversation with you on Monday. And I was like, it's interesting. Sometimes these words, they don't always come across in the right way. Okay. So what we'll do here is just like we did before, right? Where each one of you will talk. Each one of you is going to talk. Now, here's the trick. I'm not going to start with the top of the list and go down. I'm going to start with raised hands, and you'll select the term that you want to define for the class. No other person can define that term, and you can't define that term in a subsequent class. This, once everyone has gotten like these, there'll be some of them that you'll be like, wow, that one's super fucking easy. And everyone will get it, and I'll remove it from the list and we'll put a harder one in.
Okay.
That make sense?
Yeah.
Yeah, like rotation. So raise your hand if you want to answer the rotation. No one does. Oh, all right.
No, I'm being nice.
Okay, does this process make sense?
Yeah.
Are we doing this right?
Yeah.
I'll do body forces.
What are body forces?
Basically like gravity is just like a uniform force that like acts entirely on the fluid. And the most prominent one is gravity, since we're not gonna be using like electromagnetic stuff.
Anyone want to add to that? They feel good with that? Yeah, did you want to like modify the definition? You feel like there's an important part that was missed? Believe it or not, learning is a community effort. So not only is it important to learn from the book, it's also important to communicate to one another, to ask me questions, right? I don't just talk and you listen, you participate with brain, right?
Yeah.
Some of you read the book, I hope. 100%? 100% of you.
Oh.
Okay, so that was the first one. Anyone else? Yeah. Very good. Go ahead, Desiree. What does that mean? At the boundary. Is that right? Yeah. Yeah. Anyone want to add to that? Yeah. Okay. Anyone else? Yeah. Strain. Yeah. Cool. Anyone want to add to that? Okay, next. Yeah. Laminar. What does laminar mean?
Right, it's like, look at a. Flow, it's like.
Yeah.
Like flattening.
Yeah, and that's the Latin word, right? So the laminae is the Latin word for layers. And the laminar, exactly like you're saying, is layer. Anyone want to add to that? Yeah.
It's non-turbulent.
Good, yeah, it's another way of saying it, right? So you say turbulent versus laminar, those would be antonyms. Anything else? Okay, next.
The Reynolds number?
What's the Reynolds number?
Reynolds
That's a
number
tricky
is the like relative importance of advection versus viscosity in fluid.
Okay, good.
Also dimensionless.
Okay, all right. You trying to throw in a different word here?
I didn't.
Okay, all right, go ahead. Anyone else want to add anything to the Reynolds number? Yeah. Good, yeah, it's another way of talking about the same problem. Any other details we want to add here?
Scale of your patterns, depending on what you're looking at.
Oh yeah, maybe I should add that in scale lines. Anything else? What's the numbers that we think about for turbulent flows versus laminar? Yeah, 2,000, 3,000, 60,000. There's a little bit ambiguity there. Okay. Anything else? All right, next. Yeah. Very good.
I like that.
Anything else?
Can I go again with it?
No. Alana, give him a chance to shine. You shine too bright like Beetlejuice.
I don't know what that means.
Beetlejuice is a star that's gonna go supernova.
Really?
Yeah, it's a longer question. We'll talk about that later. Yeah.
The Coriolis force is a sort of like imaginary force that you kind of see happen because the earth moves underneath something.
Okay, good.
So now you're supposed
No, hold on. You're gonna add to her. You're gonna add to her. Anyone want to add to Isabel's definition?
the Cobian pilot analogy where they were throwing like a football to each other and then it was the merry-go-round.
Right.
So you can see the first couple
Oh.
of throws are gonna be lousy
Uh-huh.
because you're not anticipating.
Right, and then they'll learn,
Yeah.
right? Yeah. Everyone in class knows it, of course, as the Kobe Paolo analogy,
Of course, yeah. Yeah.
especially them.
Yeah.
They remembered it really well. We're not surprised at all that their names are said. Okay, is that it?
The Coriolis force is more important over long distances or quick speed.
That's really important too, right? So when does it become important? We can see that in these different terms, depending on how big the scale lengths are, for example. Okay, yeah.
Newtonian fluid.
What's that?
Newtonian fluid.
Hold on. No, we're just finishing up the Coriolis one. You and Kobe both. So eager. Okay, so Kobe first then, if there's nothing more about the Coriolis first.
The Navier-Stokes equation
just talks about the conservation of momentum, how, different ways to change the momentum.
Anyone else want to add to that?
I was gonna add like of a specific parcel fluid. It's like hyperfixing on one, I guess. Parcel.
This is like the most important equation.
Yeah.
Right? In fact, that's what we've primarily used. Continuity kind of comes for free, and we very rarely use the caloric equation. Okay, Paolo?
So Newtonian fluid, the fluid has a constant viscosity and no shear or stresses in it.
No shear or stresses? I don't think that's it. No shear or stresses would be any fluid not undergoing shears and stresses. Right? Constant viscosity is a great approximation. But for example, is my water Newtonian? Right? You saw it. So it moved. So
I was gonna say, Newtonian fluids have constant velocity no matter how force is applied onto it.
no, there's a more fundamental relationship here. Okay, so you apply a force to it and the viscosity changes, right? Another way of saying this more specifically is that the stress and the viscosity are related linearly. So what I mean by that is if I apply more force to a non-Newtonian fluid, the viscosity will sometimes decrease or increase. So while we said, for example, that the viscosity is constant, it's not exactly true. We say the viscosity is linear in the amount of force that we're giving it. So there's a stress relationship and a viscosity relationship that is linear, right? And non-Newtonian fluids are ones who are non-linear. Does that make sense?
Yeah,
So just a small caveat.
okay.
I don't know why I needed to spill water to prove that, but I wanted you to see the water.
Yeah.
Okay, anyone else? To add if you want to add, or we can say a word, we can move on. It's only 2 people, I think, that haven't talked. Yeah. Adiabatic, yeah. Okay. You want to add to that?
So, more so a question, by heat, would it be like there's no change in temperature or?
It's an interesting question. What do you think, Jasmine?
Oh,
Can you say it louder?
yeah, so with the adiabatic process, does that mean, you said like, that there's no like change in heat, but does that mean a change, that there's no change in temperature?
Might be a change in temperature. Good, yeah. How do we show that?
EV, that
Yeah,
is an isotherm.
yeah. Hey, that's an isotherm. T = 4. And where does the higher isotherm go? Good. That's T = 5. How do I connect them? Yeah, correct. Very good.
Yeah.
And that's called a adiabat.
Oh.
Adiabat, adabata.
So
Whatever you wanna
also temperature would. Okay.
Yeah, if I travel from here to here, that is a what kind of process? What?
Isothermal?
Isothermal.
Mhm.
Good. What is this process? It's not on the board. They're not all up there, but I now realize I'm gonna put them all up there.
Okay, so go from
ISO, same,
ISO, good.
same pressure.
It's not the same pressure.
the same volume, same volume but less pressure.
What's that?
Volume.
ISO, very, very close, very close.
Volume.
Very good, yeah.
Nice.
Okay, And then this one,
Isobaric.
isobaric, yeah. Isobaric, isoparic, whatever you want.
Okay,
Okay. Great success.
yeah,
Is there an isentropic curve on here?
That's special case in the heady band.
Yeah. Okay. It's reversible. So isentropic processes, as long as they're reversible, they're isentropic usually.
okay.
So in fact, if I can do this, pew, 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 then I could consider that isentropic. And they all could be isentropic. It just depends on whether or not they're reversible. So if heat had to come in here, right? Oops, my God, that is not a good arrow. Right? That would not be a reversible process. Unless I got rid of the heat here somehow or something. I don't know. Does that make sense? What?
That was a good Aaron.
Okay. That make sense?
Yeah.
Okay, Aaron, I think you're the last one.
I don't know what's the other number yet.
Okay, that's fine. Just pick one and then we'll see if someone already did it. You're gonna define it in however you want to define it. Hopefully right. Yeah.
Hopefully, right.
What do you mean by that? Yeah, we'll try. I mean, there may be some times when we'll hit the same one a couple times. But eventually I'll just like use a different font and strike through it and it'll stay up there so you know to know what it means. But we'll get through all of them, I think, in the next 4 classes.
Boundary layer is the difference between different mathematical regimes.
Right. Yeah. You want to add to that? You want to talk about its size, what type of physics goes on there, anything like that?
The size depends on the conditions.
Size depends on the conditions. Is it typically large or small compared to the rest of the scales? Usually small, right? Yeah. It can extend widely, but its height tends to be small. Yeah. For what though? That's very specific, right? What's that? For the wing of a plane, which is of order. Nope, scale order. How big?
Like a meter.
Meter of the order meters, right? So sometimes in physics we say very broad statements like of order, and people are like, oh, that means like how big? That's math words for big. Okay.
Scale, meters.
Yeah, approximately. Right, because remember that they're scale lengths. So if you have the boundary layer for an Airbus versus the boundary layer for a Cessna, you would expect them to vary dramatically, right? Because which is bigger? Airbus, biggest plane that you can fly, basically, right? Versus Cessna, which I can pick up and throw, right? Okay. Makes sense? Okay. Yeah, I mean, there's nothing you can do about it. Maybe. I guess we'll see. Okay, no time like the present. So, what were we talking about? We're talking about boundary layers, right?
Yeah, we were just talking about boundary layers.
Okay.
Are you referring to right now or like? What we're talking about?
No. We're talking about boundary layers in a geophysical or in a physical flow. We're talking about flow over a wing. And then we did that because we were at first talking about geophysical flows. And in geophysical flows, we had shown that we could use the Navier-Stokes equation. We could make some approximations. We learned about the Coriolis and centrifugal forces. And then we solved it, right? And then we said, okay, we're gonna learn some more stuff. We went back and we learned about, what was the second layer we learned about? Oh, maybe this is the first one. We learned about geostrophic flow. People remember that? What geostrophic flow is? You just write a bunch of stuff down and we'll see if it jogs any of the memory holes. Okay, so let's start with the fluid motion equations for geophysical dynamics. first and foremost, what approximations are we going to make when we think about the atmosphere or the ocean? Yeah. Okay, yeah, so big length scales, and is that true in all directions? Okay, no worries. Certainly good that the Earth big is one of the primary assumptions that we start with, yeah.
Oh, no, I was doing much. So the question was, what are the assumptions if we assume that the Earth is a big or?
So when we do fluid dynamics, we wrote this on the map, on the board.
Yeah.
Okay. And I told you that fluid dynamics is the art of learning what to ignore and how to make assumptions and back them up physically. And so for the rest of the 4 weeks, that's all we're going to do. We're only ever looking at special cases. Because in general, fluid dynamics, if you want to do all of the equations, you need a computer. Okay. So if you ever want to do it by hand, you're only learning about individual terms at a time. To do that, you have to make assumptions because these are too unwieldy and they're too complicated to solve. We showed only 2 examples, right, of when you could actually solve Navier-Stokes equation. And one of them was for 2 flows like this, right, a plate moving like this. And one of them was for a pipe. Is that generally applicable? No. Okay, boring. So let's think about the other places that we can use it and see what it'll teach us about those equations. So here I have the Navier-Stokes equation here. And we were learning some stuff about boundary layers and how the boundary layer, for example, the radius of curvature is large and the boundary layer is thin. Okay, when I think about the flow on the Earth, what kind of things do I want to think about? What's that?
Size.
Yeah, so we said size, so we said big. Is it big in all directions? No, it's not big in all directions. Which directions is it big in? Safe. Right? So in fact, the horizontal direction is a preferred direction. And the vertical direction is not. Right?
Like the atmosphere?
Yeah, whether that's the atmosphere or the ocean. Think about how big the Earth is for a moment. Okay. So the Earth's radius is, anyone know order of magnitude? That's correct. That's the right order of magnitude. Okay, how tall is the atmosphere? Not quite tens, but close. Hundreds.
Right.
So between 2 and 500. But most of the dynamics happens, you're right, in the tens, right? A lot of the dynamics that we care about doesn't happen above 100 kilometers. It happens right here in the stratosphere, which ends at around 40.
Okay.
Okay. So I have a preferred direction. Because if I have thousands of kilometers this way and 10 this way, right? Then the dynamics are going to be quite different. And in fact, we made a couple assumptions. Okay. So we said radius of the Earth, big, right? We have a height. Or maybe we have an ocean, and that's also H small compared to radius of the Earth, right? Okay. Look a little bit like boundary layers to you?
Yeah.
Okay, this will allow us to change what we care about in the equations, right? And we also said some stuff like we can think of the atmosphere as being stably stratified or vertically stratified, that there might be stuff that's going on in here, but that this type of motion is small compared to these motions, which are big. Why is that helpful? Well, because then we can treat any one layer like it's mostly constant, right? In properties like temperature or density, and just let them smoothly vary with some other equations, right? So if we have something like this, whether they're gradients in this direction or the other direction, we would say, well, we care more about the horizontal gradients than we do about the vertical gradients, depending on how we write them out, right? These assumptions okay? Okay. This is the equation that we have to use when it's a big planet, because it's planet curve. So we have all these. This one here, important. Raise your hand for important. Raise your hand for unimportant. Fight. Who's right? Yeah, who's right? Figure it out.
Okay,
Ask your friend.
so we disagree.
So.
And just turn to your friend, ask them a question.
Omega
Is it important?
Yeah, and then like,
Omega is changing of sun.
yeah, so it's like.
Make a friend, scoot over. Come on now.
That's the angular acceleration.
Yeah, I think so.
Because the Earth doesn't angularly accelerate.
Which one? You
I think, same with the Timothy, that's the linear acceleration.
Okay.
So if you drop those-
So with like the omega, you see how like fast it's been, and it's not changing because of this fucking, so 24 hours in a day.
Exactly. If it started changing that span, sure, that would be very important.
My initial question was like, if we're dealing with something like this big, like that, you know, something like that might actually feel.
Yeah, I think if it's, when it's, it doesn't, it's obviously that's the, just like. Yeah, I look at the rate of change of omega, there's no significant, it's no acceleration.
Yeah.
Yeah.
Okay, you guys ready?
Yeah.
This term. Is it important? Raise your hand. Is it unimportant?
Oh, I'm sorry, I'm unimportant.
Okay, why is it unimportant?
We were talking and we kind of agreed where it's like, oh, it's because, yeah, that's the angular acceleration. And the amount of hours in a day is not changing, very much.
Hopefully,
Yeah.
Right. if it is, we're in trouble.
Yeah.
And we can't let Rolanda do all the work, so is this one important? Raise your hand for this one's important. Raise your hand for this one's unimportant. Why is it unimportant, not Rolanda?
Because we're not experiencing an acceleration, and that means that the speed of the earth is gonna be constant.
Are we experiencing acceleration?
We are
Yeah. Yeah, so we are actually moving through space,
but it's tiny.
but it's small, okay? So remember, it's small. So if it's small, unimportant term. Right? So you can always look at these terms and be like, well, what's the magnitude of this, say, compared to the magnitude of this? And if this is much more important, drop it. Right? If these scale lengths or these scale velocities are small, drop it, right? Okay. Okay. So in fact, we can rewrite these terms here for a geo flow in thin rotating layers like this. What was this? What's F?
With the omega inside of it.
Yeah, might be.
Okay.
What would that mean?
If we don't care about omega, does that mean it just go away?
Oh, we certainly care about omega when we're talking about the Earth, aren't we?
Okay.
And in fact, I just want to know what it is.
What it is?
Yeah, what is the word that F represents?
I think it's like,
Foreign?
yeah, wasn't it? Wasn't it?
No,
Oh, isn't
it doesn't have an F in it.
Oh, okay.
What's that? No, not quite. It doesn't have an F in it.
No, it's-
Yeah,
As it was stated.
no.
On V,
What's that?
that's the V it's acting on.
Yeah, this is F times V.
Yeah. It's,
How do I generate U momentum? Well, with F times V. That's weird. Where have I seen that before?
Is that a viscous, term?
No, my viscous terms would be over here.
Is that you can't,
Anti-viscous.
Anti-viscous term.
because you can't like create flow horizontally without taking out like flow vertically.
Well, I can just do this, right? And generate it this way. Circular generation. So have a look up here and compare it to what we have here. Can I do my counting? Yeah.
Never mind.
Yeah, where's gravity? Is gravity important here?
The thin layer.
Thin layers, so I just threw it away, right?
The gravity's on
Is that like the, like Coriolis term?
Yes. In fact, it's our Coriolis parameter, or if it's easy to remember, our Coriolis parameter. Okay? So this is the. Okay, and notice it goes over to the right, left-hand side. This is something that is changing the momentum due to pressure gradients and viscous terms. Notice that I split up the viscous terms. What does that represent? Correct. There's very different scales. Which direction is it easier to diffuse velocity into? Yeah. So typically this will be your more important diffusion. But if I do have a lot of this velocity down here, it will diffuse up, but at a different time scale than it will diffuse horizontally. Who beans? Okay.
this substrate for both of those.
No, this is an H for horizontal, and this is a V for vertical.
Okay.
Maybe I'll do it like this. Better?
Yeah. Thank you.
Okay, and there's similar versions to this. This whole thing, of course, is equation 13.9. Is there a significant Coriolis parameter in the Z direction?
No,
Why not?
because I think if that's F times V. That's F times V, right? In the Coriolis parameter,
Mm-hmm.
doesn't V just only look at the Y component? For the velocity, the fluid velocity, I think?
I'll have you look just at 13.5 and 13.6, and you'll see there that the term itself is quite small, so it disappears. You're going to construct that one. Think about the fluid velocity in the V direction, or sorry, in the Z direction will be quite small. Right, so W is going to be a small term. Okay, so then we said we have something like this, and we could have these idea of quasi-steady large-scale motions in the atmosphere or in the ocean. And I could balance these. Remember, this is when we were talking about, for example, pressure balance between the Coriolis force and pressure gradients. This is when we learned about how to read a meteorological map with highs and low pressures and what that's going to do to the flow. You remembering that? Dust off the old brain banks, right? You remember that or no? Okay, so we made the following assumptions. Okay, we said that yes or no? You remember this? Yeah.
Why even negative come up in the right side of that?
That hurt your heart? I mean, what it is that this term up here has a negative, and this term up here has a negative. And what I'm showing you is that the viscous terms here, we're going to ignore. And these advective terms, we don't need. And you have a balance between the Coriolis parameter and the pressure forces. Right? So that is called a geostrophic balance, when there is this balance between the two. And you get a fun number called the Rossby number. What's the Rossby number tell us?
Sorry. But as far as, FB and FU are the two components of the,
Say that again?
for FB.
Yeah.
and FU, are
Yeah.
those components that come from B?
From V,
Yeah,
the vector U.
yeah, oh, okay.
Like that.
Like that, okay, there we go.
And here's my coordinate system. Yeah. Okay, so we had the Rossby number. And it was a ratio of the nonlinear, which scales like U squared over L, to the Coriolis term, which scales like FU. Last time I'll say it, don't worry.
Yeah.
Okay. And we recall that this led to this really fun property of the motion of, say, a high and a low pressure system. Right? If I draw it like that. So how would I connect those two? Traditionally, you'd say if I have a high pressure system and a low pressure system, I would expect flow to just go like that, right? Is that what happens in geostrophic balance? No, it gets deflected, right? Gets deflected by the fact that the Earth is rotating, just like our Kobe and Paolo example, right? Just like that.
Yes.
Exactly the same. Okay.
Gotta use it.
What's that?
Go to a merry-go-round.
Yeah, that's the work. I thought you did that already. And go to,
Like that in real life.
oh, we need to watch them from above with a drone. We got to buy a drone in order to do this. Yeah. Okay. How does the flow circulate around high pressure systems? What are you doing over there?
Doing this in high point.
Your H looks like.
That's what your age looks like.
Which H? This one here or this one here?
The one that you were just working with from the high.
Your H looks like. what?
That, is that better?
No, over there.
TIE fighter?
Yeah.
Yeah.
Is that better?
That's good.
Now they're more engaged, right? They're definitely learning more. They're not distracted. Okay, so how does the flow circulate around a high pressure system?
Either, yeah. If one goes one way, then the other one goes the other way.
Good, and we just need to know one of them, right?
Yeah.
And if it's stuff,
And in the south, it's the opposite. Good. Perfectly round circles. Good. Force pressure balance, right? Okay. So we understood all of the assumptions that went into that, and we can use that world now to understand a boundary layer in a geophysical flow. Okay, so let me show you this picture. Ready? Okay. You have big ocean. Ocean big. You have a prevailing wind. People know what a prevailing wind is?
I guess
A wind that never fails.
Yeah, essentially. It's a consistent wind. So you go outside today, sometimes you feel it in front of you, your hair goes back all nice, right? Your hat comes off, okay? Skirt, whatever, right? Shirt, oh, right? Okay. That is not a prevailing wind. Those are gusts, right? Quick bursts. That is not prevailing. If you move off of the boundary layer, you have no turbulence. What you're seeing at the ground is the turbulent flow, which can result in gusts, right? Okay, so let's move off the boundary layer. And let's say you have like a flow that is just continuing, like that, flowing like a river. Well, it turns out that winds do that too. We don't think of them as rivers, but in fact, we saw that when we saw atmospheric rivers, right? A couple months ago. So you can have a prevailing wind, which means that it keeps blowing in the same direction all day long, all night long, roughly the same speed, okay? And then the question is, what happens to that wind's profile as it comes into contact with the water? Because there is molecular contact there. They're not allowed to mix. And the surface here, we're going to assume is not perturbed by large waves, okay? Even though winds, of course, create waves. I hope everyone remembers that. We're going to think about what does it do starting from the surface of the water to the entire water and going down. Okay? So what does that mean? What do we expect to happen? We have wind blowing to the left, yeah.
It's gonna be
Well, the wind, of course, can't go through the water.
Right.
Is that what you meant? No.
Yeah, it's not gonna. It's not gonna.
Okay, so let's draw the picture really quick. Okay, this is the boundary. Okay. Wind is blowing this way. Now what happens? I'm not going to draw an undulation, even though that is correct. This will be large enough that the undulation will be small.
Oh, it's
Sheer.
Okay, so there's a shear, there's a contact surface. So let's put the contact surface here. Okay, we're gonna call that x equals 0. Or maybe z equals 0 for.
it's fair to treat like the. I guess the air as like it goes into the conveyor belt. And it would be something like a similar effect to like when we described a wall.
Sure, okay, so now we have this intuitive sense that it should pull. And it should drag the water with it. You have a question?
Is there a zero slip on water?
Yeah, that's a good question. Is there a zero slip on water?
Yeah, it's like that. There's beliefs that it's a case.
What was our last, I'm sorry, no, but wasn't our last like zero slip thing just like inside the water? But now it's like the interaction between water and air.
Yeah, so before we had this idea that we had flow moving past a flat object that couldn't move. Can the water move?
Yes.
Yes. So in fact, if we had a no slip condition, would it do anything to the water? No. So if the velocity went to 0, then the water wouldn't move. But I'm going to tell you that the water moves, and the no slip condition is going to change slightly.
Maybe that the water and the air have to be the same velocity at the surface.
Right. So that was the different version that we had before. When we move the whole plate, it drags the water with it, remember? And they have this infinite plate that moves to the left that changes the water. So we'll do the same thing, but now it's not a plate, it's air. Okay? And before we had an infinite plate and all we saw was a similarity scaled solution. Now we're going to introduce the fact that it's in a geophysical context. Okay? So our expectation is that maybe, in fact, it goes down, but it's non-zero. And the velocity here, even though it's a different medium, has to be the same. And then the question is, what happens after that? Yeah. Good. Okay. So you think that it encounters more and more resistance. Okay. So we'll use that idea. We'll say that the depth matters. Anything else matter?
The difference in viscosity between the.
Sure. Yeah. If you had a very thin fluid, it probably could communicate that layer lower. Okay. Anything else? Yeah. Yeah, this Jesus Christ. Someone spilled water on the ground. This velocity up here, the one that goes back out, is going to be driving the whole phenomenon. That's obviously going to matter, right? Anything else? Okay. Sorry, it's not me. I mean, it is, but it's not. Yeah.
I mean, there's a chance that like maybe the water is going the same direction.
Water will not go the same direction.
Yeah. Yeah, it could be like going into the board, out of the board.
Oh, that's sneaky. I don't like that at all. Okay.
You cheated.
You cheated. You looked at the picture that's on the wall. Okay, so in fact, yes. Remember I told you we'd learn about a hodograph. Okay. And the hodograph, they're actually pretty fun. They are this picture in the bottom, and they will describe the fluid velocity as a function of depth. So it's a UV graph. We'll talk about that in a few seconds. But let's talk about how we get there. Okay. So in a steadily, so we saw two examples already, right? We saw the friction balance with the unsteady acceleration. Remember that? Moving plate. We saw the advective acceleration with the Coriolis force, right? And now I'm going to show you a balance between Coriolis acceleration and friction. So we're going to use the fact that you have a medium here that is communicating velocity through friction, and it's going to be balanced by the rotation, Coriolis rotation. Okay. No one's cheering, so I don't know if you did. Okay. Whee! Okay. So let's write the equations of motion. Like a V.
Pretty sick.
Cool.
No, I promise I wouldn't say it, so I'm not going to.
Got it.
You know why. Can't be trusted with these words. Okay. So here's our equations of motion. So the generation of fluid flow is coming from
Diffusion. Diffusion. The diffusion of the.
by,
Okay.
that's what these words mean. Right? Okay. So let's define Z on the surface there equals 0, which I did. What are the boundary conditions?
Boundary conditions at, right when we equal to 0, do we have different like labels for like the velocity of the air and velocity of the fluid?
We won't need to.
Okay.
We're not gonna think about what the flow on the top is. The flow on the top is prevailing. We're not gonna build the next one.
Oh, okay, okay.
Got it. Just to review one more time, what were those two equations about describing again when we were taking those other two?
Wasn't it?
Hold on. You know everything. You let someone else. I'm gonna keep writing boundary conditions. You look around and you tell me if you can define them. If someone else can jump them. Not wrong.
No.
What do you mean? How'd I get them? Did I conjure them from thin air like a magician? What's that read?
They're right there.
They're right here.
Got it.
So there's 3 of them, and I didn't write them down because I referred you to the book where the other 2 are located. There's one for DUDT, there's one for DVDT, and there's one for DWDT. And they have slightly small differences, but the major difference for DWDT is that it doesn't have this thing. Okay? In this particular circumstance, I only want the U and the V. Okay? And I'm going to solve that at every level. And I'll show you how I solve that. Okay? So here, I said, this is what I wanted. I want a balance between the Coriolis parameter and the viscosity. I don't yet care about the pressure gradients. Not going to set up pressure gradients here. Okay? So let's throw them away. Right? To make our lives easier. This will be a steady state, non-advective problem. Let's throw those away. Okay? I just want a balance here between these 2 things that I think are related. And we'll see whether it creates something meaningful, something that I can learn about. Okay? What does this first one say? Let's try the last one first. What does this one say? You can read it. UV go to 0 as V goes to minus infinity. Right. That's what we said over there, right? We guessed that would happen. What's this one?
Is these still a horizontal component here, or is it?
Yeah, so what's the coordinate system here?
Our coordinate system is like having a horizontal at Z.
Yeah, so Z is depth.
Yeah.
Always.
Then why did you?
Why would you do this to me, Mateo? Stop learning me.
Okay, that makes sense.
So what is D, V, D, Z? Yeah.
Does it change in velocity? Stop changing as it is.
What does that mean?
It has to be equal in water.
Yeah, we can't have a velocity gradient through the water, can we? That's not very sensible.
Yeah, with especially with our conditions. I think, with
Right.
conditions like that.
It can increase, right? You can have it be 0 and then go off to do something later, but it's got to go to 0 at the boundary. Okay, last one's the hardest one.
Oh, the first one?
Are we just saying that at z equals 0, we're gonna get some constant that relates to this other side? That's it. That's all we're saying.
So this is essentially saying this is how hard the wind is pushing. How? Make sense? Notice how we have to make these statements. They're kind of obvious, they're kind of annoying, but as long as we state the problem fully, we can just come to a solution quite easily, okay? So what I mean by that is, I see something up here. I've got a FV and a double derivative, and an FU and a double derivative, and I am gonna do something that you're gonna absolutely hate. Okay? I'm gonna think about it, and I'm gonna guess the solution.
Oh,
What? How does he do that? He's so smart. No. So let's learn how we do this. We'll do this first by something called complex superposition. Okay? So what does that mean? It means that we're going to make this the following statement. V, capital V, is now going to mean the complex conjugation of these two parameters. Can I do that? Yeah, why not? You do whatever the fuck I want, right?
as long as you still have the boundary condition.
Well, it's not that this has a boundary condition. We will show that there is a relationship here because the way of my differential equations having a double derivative lends itself to a wave solution, does it not? And in fact, we saw a deep relationship between waves and exponentials. And exponentials fall off as a function of depth. We saw that when we were doing gravity waves, did we not? So we might end up using a lot of the shit that we've already seen. Amazing, maybe even stuff that we've done in the homework. Okay. Yes or no? People have done the homework. Yeah, yes. I'll myself off this words later. All right. So in fact, I could rewrite this equation. Okay? Because all I have to do here is I can add them together and I can multiply 1 by I. And I'll get the following differential equation. Anyone tell me if that's true? Did I make lie? Don't think so. In fact, there's a U over here. And there's a V over here, is there not? And my definition is U plus I V, right? Okay. Multiply that one by minus I. Or by I, sorry. And then I add them, and I get that.
Yeah.
What's the solution?
The thing in front of the B is just a constant. Place of positive B is constant.
Okay, yeah, so I could think about this in terms of like I beta if I wanted to. I'm gonna keep the I, because that's gonna tell me something important, right? But there's enough there that I might not end up doing that, but I didn't think about it that way. What's the structural changes here? What's the mathematical pieces that are giving me the hint to the solution? V is on both sides and
There's a double.
well, there isn't, right? If there was only one there, what would you say?
We're looking at.
No, let's say you had D, D, Z, X, let's try this one. Okay, totally separate world, they're not related at all, don't think about this too much. Okay,
Oh, that's like EQL.
what?
That's like EQL.
So what is A?
EQL.
You just guessed it,
Got it.
is that correct?
Yeah.
No. What are you missing?
Plus C. Plus C.
Maybe,
It's constant.
yeah, like a, yeah, like that. Okay, so does that mean that we found with B is actually?
Try one more step. Try one
Okay,
more step.
sorry. So sorry.
Don't worry, it's not your fault.
Does that mean that we'll get like beta squared for the,
And now you get a beta squared,
yeah,
but there's no beta here.
Oh, it's EVX over this.
The beta was here now.
yeah, but wouldn't you have to, in order for it to be the same, we have to like.
Is this still valid?
We put beta in our exponent,
If the beta goes in the exponent, what happens to the beta?
it becomes squared.
It comes out.
Yeah.
Is it out here?
It's not,
No. This is just learning that exponentials solve this form.
okay,
There is stuff in front, so you're right that there will be a beta that we'll put in later. But I'm just showing you that when you see this, think exponentials. And more importantly, think complex exponentials. Because they will just come right out. So let's try it out. Let's try a solution, okay? Let's try what? What's my solution? Didn't even ask for specific kind.
It's the failure of IDLs.
yeah.
Okay,
Yes.
you like adding constants to the end? I like adding them somewhere else.
In front, like I did.
In front, yeah, so let's call this,
Here.
okay, yeah, so I could do something like this. Are those both valid? Have to be, right? So this is the general solution?
Yeah.
But of course, it doesn't matter, because that's what I wrote over here. So I could write this better. Let's write this for the actual problem that we have, and not this random other problem that is somehow not related at all, right?
Yeah, totally not.
Totally not related at all. What's the general solution? Let's see this. No, this is just a normal delta, and the delta you'll see has the things that you already know about. Be right back. Hold on. So we write beta before and he's writing delta. Why did I do it this way?
Why did you have the delta? Because it's either, you know,
No, sorry, why did I have this?
hold on.
Instead. And you take the version of it. Both of those. I guess, yeah. And then after like cleaning it up a little bit, you'll probably just have stat out.
Probably will have that stat out. So I need the other ones didn't have it. They just did beta. I gotta be careful with the way that I set up the complex exponential. But it's okay. To see that by inspection. Take two derivatives. Take one derivative and you get.
1 plus I.
1 plus I over delta,
Oh,
right? Over here. And then minus 1 plus I over delta here.
Right.
And then I do it again, I get another version of that. Now I get this parameter squared. Oh no, that's the big problem. No, because I squared is minus 1. And the 1 is minus 1 by 1, 2. Eliminate each other. And I'm left with something with I in it, which is what I wanted. And I'll have two copies of that, right? What does this thing equal? Let's do this really carefully because I know sometimes brains don't like they're on Mondays. What's that?
that there's a, would it be 2 on it? Yeah. there we go.
Oh, and look what comes out here. Almost like I thought about that ahead of time.
We did.
Right, so these things do. By times.
Okay, fine.
And this thing out here is the thing that I wanted to match up with the thing. Okay. Does this have any physical meaning? Or is this all just mathematical mumbo jumbo?
Since they're conflict, I can write them in my pocket.
Yeah, you could do that. You could write them in terms of cosine and sines. What's that? Sine and cosine are waves, yeah. But also we know that exponentials, they decay exactly like we want to here. So we have some boundary condition here that we could apply to a brand new fancy solution. Why would I want to apply boundary condition here?
So you find the particular description.
Right, so what's the first thing? So I have a couple things that I don't know. This is all defined by the parameters in my equation, so I'm not worried about that. What are the things that I don't know about my solution? A and B, right? So we need at least how many boundary conditions? Two. Do we have that many? Yeah, in fact, we have more, right? So we should be able to fully describe this flow. So which one is the one that we're gonna get rid of first? Which one? Yeah, why is B bad? Well, yeah, negative here is bad because
Means that like the final outcome of it would be. It would have that form of negative, right?
I'm tracking.
Yeah, I'm trying to make it better. There would be like the same answer but negative instead. Is that what ended up happening?
Well, these are different answers.
We want it to decay, right?
You want it to decay?
Z's already negative.
Z is already negative,
There we go.
and this term here becomes positive. So this is not a good term.
Bad term.
Bad term. B for bad term.
Perfect.
So all I have to do is define A. That seems easy. I got some other stuff up there, right? What would I use?
It's used.
What? Second one doesn't. Oh, yeah, might be something. Won't give me what I want.
We don't want lunch.
Get this one. This is what I want. Because this is relating to something that I have.
Yeah.
Right? A boundary condition of the fluid flow. This one is like a kinematic boundary condition, says I can't move, I can't jump the flow through. And we'll use this to make sure that other things work later. But let's use this right now because it has this thing here that's pushing. That was like a function of the original flow, right? So I can use that and I could just turn A into what it is.
Is that easy to solve for, with lease of B there? And replace it, or,
No, V sub V is a property of the flow.
oh, okay,
The only thing I'm doing here is I have a definition for you. I take a derivative with respect to Z,
oh,
right?
that's right.
And I
Okay,
know that it'll have to be equal to tau, and then I just solve for A.
got it,
And that'll give me something as simple as A is 1 minus I tau delta over 2 rho nu. Okay. So you can combine these together, you can put this stuff back into here to get U. To get V. Is that really?
Yes.
When you get an Ekman layer, increases the function of height. So the exponential here squishes it down as a function of Z. Okay. And you'll also see that as you go through the flow, it starts to curl because there's a cosine attached. Right? A sinusoidal function attached. And that's from the rotation from the Coriolis force. Okay, I've run out of time as usual. I apologize. We will finish this definition on Monday. And we'll do another example of what happens to an Ekman layer at the bottom of the ocean, for example.
Thank you, Professor.